Welcome to today's live interactive session on the subject mechanics of fiber reinforced polymer composite structure. Today we are not going to discuss any sample problems. It is just a revisit of all the topics and all the concepts that sir has taught in the class. So it is kind of a summary class. So let's start. So the first thing is what is composite. So composite materials have two or more different constituents. As you can see in the diagrams, it there are two or more constituents. Like in the concrete, it has a mixture of adhesive aggregate giving a rubber strong material that is very widely used, as well as it can have mostly two, that is a reinforcement and the matrix. So in a composite material, the matrix phase is continuous but less stiff and weaker, while the reinforcement phase is discontinuous but more stiff and strong. As you can see in the diagram, the reinforcements are mostly fibers and polymer, and it has a polymer matrix. So when we combine a reinforcement fiber and a polymer matrix, we get a fiber reinforced composite. And here you can see matrix. When you will cut this the composite, you can see on the surface, as you can see here, that the matrix is a continuous phase, whereas the reinforcements are discontinuous phases where they are separated from each other because of matrix between them. So that is a fiber reinforced composite. Next is the constituents in a composite combine in macroscopic scale, whereas those in alloy combine in microscopic scale. As alloys are also a component which contains two or more constituent elements, so to differentiate between an alloy and a composite, the main difference is that the level at which it is combined, that is macroscopic level when it is combined it's a composite, whereas microscopic level when it is combined it's an alloy. And the reinforcements generally act as the load-bearing members, whereas the matrix acts as the binder, which binds the reinforcement fibers with each other. Next, we can take one composite. Next, we will discuss the stress-strain relationships of the composite. So, each component and the So a substance which has different properties in different directions is known as an anisotropic material. So composite. So first we will define different materials that are present in the environment. So first thing is an anisotropic material. That is when we take a small structure of that material, the properties of that material are different in all the directions. So because of that, we get 9 stress and strain components of that material, and when they are defined, the relation is defined with each other, we get the generalized Hooke's law, as you can see here, where the stresses and strains are related to each other by a matrix, and this matrix is a 9 cross 9 matrix, as there are 9 stress components and 9 strain components. So when combined them, we get a coefficient matrix, which is a 9 cross 9 matrix, and it is a fourth order tensor, as it is 3 to the power 4 is equal to 9 cross 9, hence it is a fourth order tensor. And these, when stresses are defined in terms of strains, which you can see here in this matrix, then this is known as a stiffness matrix. Whereas if strain is defined in terms of stress, then it is known as a compliance matrix. Now there are different types of materials: isotropic, anisotropic, monoclinic, orthotropic, and transversely isotropic. So first we talk about anisotropic material. It is when the property of a material which allows it to change or assume different properties in different directions. So an anisotropic material will have 21 independent elastic constants. As all the coefficients of this stiffness matrix will be different, their value will be different. But as there is a symmetry from the diagonal elements, therefore we consider 21 independent elastic constants. After anisotropic comes monoclinic, which is elastic solid has one plane of material property symmetry. So in a monoclinic, there is one plane which has a symmetric material property. So in that case, for a monoclinic, the number of independent elastic constants will be 13. It will reduce from 21 to 30 when we go from anisotropic, which has no symmetry at all, to a monoclinic, which has one plane which has material property symmetry. After monoclinic comes the orthotropic material, which has all three planes of material property symmetry. So for an orthotropic material, the number of independent elastic constants are decreased to 9, which is after 13 it comes to 9, as there are three planes, all three planes have symmetry to each other. After orthotropic comes transversely isotropic, which has three orthogonal planes of material property symmetry, and one of them is a plane of material property isotropy. That is, it is same kind of like orthotropy, but one of the plane of it is isotropic. That is, it has similar properties in all directions. In that case, in a transversely isotropic material, the number of independent elastic constants is equal to 5. And the last is an isotropic material which has properties remain same in all directions. So it will have only two independent elastic constants, that is the Young's modulus and the Poisson's ratio. And so it will have total two independent elastic constants. And there is a shear modulus also a property, an engineering constant which we consider, but it can be defined with the help of Young's modulus and Poisson ratio. So we consider only two independent elastic constants, and the shear modulus is dependent on those two properties. Now, when we shows different material properties in the compliance matrix, which is a matrix of the stress strain matrix of that material. Then there are certain parts in the matrix which can be differentiated as extension coupling coefficients, shear extension coupling coefficients, shear coefficients, and shear coupling coefficients. So as you saw before that there are different independent elastic constants for different materials. So if the independent elastic constants are decreasing, so some of the coefficients will become 0, and the reason where the coefficients are becoming 0 can be so each material property can be defined according to which property coefficients are getting 0. As you can see, a fully anisotropic material, that is all these coefficients will be non-zero. So the whole matrix will be a non-zero matrix. Whereas then comes orthotropic material, as it has independent variables 9. So here all the shear extension coupling terms will be 0. Then monoclinic materials, which has some of the shear extension coupling terms as 0. As monoclinic has 13 independent elastic constants, so some of the shear extension coupling terms, here you can see these are the shear extension coupling terms, they will be 0. And some of them will not be 0. So if the whole shear extension coupling terms are not 0. Like orthotropic. Whereas next comes transversely isotropic material, where all shear and shear extension coupling terms are 0. That is shear coupling and shear extension coupling terms are 0. These two coefficients. And last is isotropic material, where all the shear extension coupling terms are 0. This is same like transversely isotropic material. Now we come to a composite. How a composite is formed? That a fiber and the fiber which is reinforcement, and the matrix which are mostly epoxies and unsaturated polyesters. Those things make the matrix. So when a fiber and the matrix, the reinforcement and the matrix combine, they forms a single lamina. So a unidirectional lamina, that is all the fibers are in same direction. Then that lamina is heterogeneous and anisotropic. So what does that mean? So heterogeneous means that the properties are location dependent on that lamina. Whereas anisotropic means the properties are different in all the direction and they are direction dependent. Now, mostly we talked about orthotropic laminas when we studied. We didn't go anisotropic as there are a lot of properties that we have to define. So we mostly considered an orthotropic lamina. So orthotropic laminas are also of two types, specially orthotropic lamina and generally orthotropic lamina. Specially orthotropic laminas are those which has the analysis axis XYZ coincide with the material axis 1, 2, 3. As material axis are the axis which is formed due to the alignment of the fibers in the lamina. So when they align with the global axis XYZ, then it is known as specially orthotropic lamina. Whereas generally orthotropic lamina is when the fibers are aligned in some other angles and they don't coincide with the global axis XYZ. Then it is known as generally orthotropic lamina. So here you can see it is a stress strain matrix of an orthotropic material when which is defined in terms of engineering constants like modulus, Poisson ratio and shear modulus, which can be easily measured by using a universal testing machine. So these are the engineering constants that we can find experimentally, and by getting these values we can form the whole stress strain matrix of an orthotropic material, as you can see here. Next is here you can see this is strain in terms of stresses. So this forms a compliance matrix. As I said before, this is a compliance matrix. But an orthotropic material lamina, when we consider only two directions, and the third direction we consider it as very less width. So when we reduce the this whole stress strain matrix into the terms of only stress and strain in what two directions, one and two, considering this third direction as very less, so we don't take properties in that direction. So when we compress this matrix, then we get the reduced compliance and stiffness matrix, as you can see here, which only considers the stress and strain in direction 1 and 2. So this is the reduced compliance and stiffness matrices. Now reduced compliance stiffness matrix can further be transformed by using this condition, and this transform reduced matrix is done when we have to define the properties of a general orthotropic material in terms of the global axis. That is, when we are given given a lamina which has materials in certain angles, and we need to define those material properties in terms of the global axis XYZ. At that time, we have to reduce this compliance and stiffness matrix by taking this transformation matrix and multiplying it with that, and later we can get a transformed reduced stiffness and compliance matrix, as you can see here. So these are the direct equations to find the different components of the stiffness matrix, and here to find the different components of the compliance matrix, which gives us the transform reduced stiffness and compliance matrix. And these values can be calculated in terms of the coefficients of the reduced compliance and stiffness matrix. And also, this is the transformation matrix that is used to change the conditions from global axis to principal axis or material axis. Now comes failure theories. As when there is some composite form, it can fail, and to understand those failure, there are different theories, mostly differentiated into non-interactive theories and interactive theories. In non-interactive theories, we get maximum stress theory and maximum strain theory, whereas interactive theories, we get Psi-Hill theory, Hoffman failure criteria, and Psi-Gu theory. Mostly, we discuss the maximum stress theory and the Psi-Hill theory. So, maximum stress theory is when the different stresses value should lie between these ultimate longitudinal and transverse strengths of that lamina. So this is the property that defines the maximum stress theory. So if the properties of the lamina we considered doesn't lie in this condition, then it will fail. Similarly, this is the equation that we consider when we have to study the Sahil theory failure. And also, even if the lamina is not failing, we can find the the direction and in which there is the maximum chance of failure by taking the stress ratios of that lamina in different direction in means longitudinal in longitudinal direction or the transverse direction or in plane shear, in which condition the lamina will fail the first. We can find that by calculating the stress ratio, but stress ratios of those components with respect to their ultimate values. Next, we talked about the concept of volume fraction, as every composite is formed with the composite has the fiber and the matrix, so there is certain percentage of fiber in that whole composite and some percentage of matrix in that composite, that what combines the whole composite. So it has certain characteristics, as if the fraction of fiber is less, then it will fail first, because matrix doesn't have much strength compared to fiber, but excessive fiber is also not good. Even though volume fraction of the fiber increases, it is beneficial for the composite, but too much fiber is also not good, as there will be less bonding between them, as the amount of matrix will be less, as the volume fraction of matrix is less. So considering those components of volume fraction of fiber and matrix, we can also calculate the modulus of the whole composite if we know the modulus of the fiber, matrix and the volume fraction. So therefore that there are two different equations to find the longitudinal Young's modulus and the transverse Young's modulus. So to find the longitudinal Young's modulus, this is the equation you can see at the left side, whereas to find the transverse Young's modulus, this is the equation. Also to find the shear modulus, the same kind of equation like the transverse Young's modulus is used. But then we found that the experimental values of the transverse and shear modulus is very different from that what we found from these equations. So that so uh, because of that it was defined in another way of finding the transverse and shear modulus, that is Hazen method. So here you can see this is the equation for that, where m is the modulus that we need to find. M is the modulus of the matrix. Eta value you can define by the modulus of the fiber and the matrix, and zeta value is equal to 2 for when we have to calculate the transverse modulus evaluation, and 1 when we have to calculate the in-plane shear modulus evaluation. Now, as I said, the amount of fiber and the matrix is very crucial. That can and it defines the properties of the composite. So there are two uh, volume fractions that we have to consider. One is the minimum volume fraction and the critical volume fraction, fiber volume fraction. So once the fibers have broken in a composite, the stress that the matrix can take alone is given by the ultimate stress of the matrix into the volume fraction of the matrix. And only if this stress is greater than the ultimate tensile strength of the whole composite, it is possible for the composite to take more load. So the volume fraction of the fiber for this whole condition is possible, is known as the minimum fiber volume fraction. And this is the equation to solve it. Whereas it is also possible that by adding fibers to the matrix, the composite will have lower ultimate tensile strength than the matrix. In that case, we have to find the volume fraction for which this condition is possible, and that condition is we find the volume fraction will be the critical fiber volume fraction, and this is the equation to find the critical volume fraction for this condition. Next is the effect of moisture and temperature on the lamina. So every composite can react with the environmental conditions, and the most frequently considered environmental conditions are the moisture and the temperature. So whenever there is a moisture accumulated in the composite, there is certain change in the strain of that composite will expand, and when and if there is a temperature change, according to the coefficient of the temperature expansion, the matrix and the fibers will expand accordingly. So to find that, so there is some expansion because of the temperature and the moisture. So any expansion relates directly to the strain component. So these are the equations which relates the strain in xy direction with that of the coefficients in xy direction and the change in temperature or the concentrations. Next we move from one laminar to a laminate. That is when more than one laminar combine to each other, then it forms a laminate. So mostly we consider an orthotropic lamina where the direction dependent properties could be controlled or tailor made by changing types of fiber matrix, and for a given fiber matrix combination by changing fiber orientations and fiber volume fraction. All these conditions we can take care while forming the laminate. So whenever we see a laminate, the first thing that should come to our mind is the ABBD matrix. ABBD matrix is what defines the conditions of the whole matrix, and it is a matrix which forms the relation between the moment, the resultant force, the mid plane strain, and the curvature of the whole laminate. So as you can see here, N, X, Y, and X, Y, these are the resultant forces. M is the momentum force, the moment. E naught is the mid-plane strains of the whole lamina, as we always considered the midpoint of the whole laminate, and according to that we consider different properties, and then there is curvature. Now to find the strain of each lamina, this is the equation to find the strain of each lamina. It depends on the mid-plane strain of the whole laminate and the curvature of the laminate and the position of that lamina in that whole laminate. Now the ABBD matrix, this how to get this matrix, I already showed an example in the last session to how to calculate them, and these are the direct formulas by using which you can find the A, B and D matrix. As you can see here, A matrix, for that we need to do the summation of the reduced stiffness matrix of all the laminas, and it needs the, and we have to subtract the position of that lamina. Whereas B matrix is equal to half of the summation of the reduced stiffness matrix of every lamina and the square root of the summation sum summation of the square root of the position of the lamina, and similarly for D matrix is 1/3 of the summation of the reduced stiffness matrix, and Q summation subtraction of the cube root of the position of that lamina. Till now, we only talked about the in-plane stresses on a laminate. That is, we considered that in z direction, the thickness is so less that there is no change in the properties. So we only considered the change in properties in the x and y direction and the shear stress because of the change in x and y direction. So all the stresses in x, y direction and the shear stress in x, y direction, these are the in-plane stresses. But when we consider the z direction, then we get other more stresses, that is the out of plane stresses. Those are the shear stress in z direction, the stress in z direction, the shear stress in xz and zx direction which are symmetric to each other, and the shear stress in yz and zx direction which are also symmetric to each other. So, in conclusion, we get stress in z direction, shear stress in xz, and shear stress in yz directions, and these all are known as the outer plane stresses. Now, these outer plane stresses also depend on the in plane stresses. As you can see, it is already defined in the classes how it depends on it. But in conclusion, the shear stress in xz direction depends on the shear stress in xy direction, which is an in-plane stress, which we already know how to calculate. So from that, we can get the value of the outer plane stress, shear stress in xz direction. The out of plane shear stress in yz direction depends on the value of the stress in y direction, which is an in-plane stress, and the stress in z direction depends on the stress in y direction. So from knowing our in-plane stresses, we can find out the outer plane stresses. And these outer plane stresses are those which are responsible for delamination of our composite. Now, there are two kinds of matrices we considered. That is, one is whether it is 0 or 90 uh, ply directions. So for that there is will be no shear. When the laminas are when the fibers are aligned in 0 and 90 degrees, then there will be no shear among the laminas. As there is no shear stress, that is tau xy will be 0. So we won't get any value of tau xz, but there will be stress in y direction. So out of planes stresses, that is tau x yz, and stress in z directions we can find for 0 90 laminas. Whereas when it has some angle, then these are the properties that are followed for a laminate which has fibers aligned in certain angles. Next, for it, when we consider the whole composite, there are certain properties which which are defined for the whole composite, like the transverse deflection of the composite, the buckling loads, and the natural frequency of transverse vibration. So, first is the transverse deflection along z direction, which can be defined by this equation. The derivations are done in the class. So, this is the final equation we are getting. And for a specially orthotropic symmetric laminate, where the B matrix will be equal to 0 and the D16 and D26 coefficients are equal to 0. This is the final equation we are getting, which shows that the transverse deflection of the laminate depends on the coefficients D11, D12, D66 and D22 of the depends on these coefficients. And we consider the simply supported boundary conditions along the edge where x is equal to a. So this is the simply supported boundary condition for a laminate rectangular plate of dimension a cross b. Then the buckling loads. This is the final equation of buckling load, and when we consider it for an orthotropic symmetric laminate, this is the final equation we get, which again the equation depends on the coefficients of the D matrix D11, D12, D66, D22. And finally, the natural frequency of a transverse vibration can be found from using this equation of a laminate. That's all for this session. Thank you.